Now I'm going to continue basically what I started at the end of last lecture. So I'm going to talk a bit more in detail about this notion of Krylov complexity. And then I hope to be able to guide the lectures in the direction of thinking about gravitational systems and how all those things manifest themselves and are useful when thinking about gravity, in a particular holographic gravity. And that will be obviously the main subject tomorrow in my last lecture. So we have been already introducing this idea of Krylov or K complexity. And I will go in a little bit more detail. Although, again, I should say that there is a lot of detail in this subject. It's been a very active subject recently. And so if you want to know more of these details, then you can look at our recent review, which we put on the archive like a month ago or so. And this is with Eliezer Rabinovich, with Ruchir and Adrian Sanchez Garrido. So, so the way that Krylov complexity was, in some sense, first introduced, I think there's many waves of people working on Krylov, essentially started, by the way, as a set of numerical tools, I would say, by Krylov and also by Lanczos, who had a lot to do with it, but whose name hasn't made it into the title of the object. But anyway, so I'm going to start developing it by thinking about this idea of Heisenberg evolution, but I'll emphasize that also that similar statements can be made on Schrödinger evolution. So in this case, let's look at we want to look at, for example, complexity or growth of some Heisenberg operator. Oh, and in that context, we look at something that has just been mentioned. We look at the Hilbert space that corresponds to the space of linear operators acting on a given Hilbert space. So we have like some quantum system, sigma, with a Hilbert space H, and then we look at the space of linear operators acting on H. And I call that space H with a hat on it. Okay, so it's what Tomáš was calling the space of endomorphisms of H. So you have basically that O acts on the original Hilbert space, and I associate with that a state O that I denote like this. So it's almost Dirac notation, but with a round bracket. And so O is an element of this H hat. And of course, in order to be considered a Hilbert space, which, by the way, is again well established in the theory of Hilbert space, and maybe I should also say Banach spaces here, but you can read it, for example, in the standard books by Reed and Simon. But you need an inner product, and the inner product is actually following. So if you take O and let's say I'm really so bad with breaking these chalks. O and W as elements of this H, then the inner product will be O, W, and I can choose it to be, for example, the two-point function, if you want the trace with respect to some state on H of O dagger with W. And for example, I can say rho might be the thermal density matrix. I could have said this is a system with Hilbert space H and Hamiltonian, so Hilbert space curly H and Hamiltonian normal H. Or I could also just look at some particular excited state density matrix, or I could think of other inner products, other states that are used for this inner product. But this one here is the one that is used most of the time. Often one considers the infinite temperature limit. Now, Krylov space K And its basis is basically the following. So now Krylov space, which I might call Krylov space, let me denote it by curly K, and I'll denote it by O because now it depends on the seed operator A. So this is going to be the span of, well, O and then H with O, and then H with O, and so on, which potentially terminates, well, I'll just say and so on here. And so then a good basis for Krylov space we will denote by essentially now counting the number of commutators that I have. So, 0, I guess I'll draw it like this to distinguish it from my operator. 1, 2, and so on, where essentially this is obtained from that by, well, let me write Gram-Schmidt in inverted commas, because actually what we use is the Landshor's algorithm. So he did make it into one commonly used term in this subject. So Landshor's was a Hungarian mathematician who actually also will appear in the gravity part, because he also thought about general relativity at some point in his research career. But here, this is algebra. So the input for this. So let me describe now this algorithm. So that's okay. So in this subject, I should say again, we're interested mostly in chaotic dynamics, and chaotic dynamics are typically very, very hard to solve. Fortunately, you're just following a set of lectures before mine, for example. One of the rare examples where you have, like really non-trivial chaotic systems that can be solved. But often one either makes general statements or tries to find useful numerical methods to deal with things. And this Landshor's approach actually, I think, lends itself to both. But it's described in an algorithmic way also because it lends itself often to numerical studies. So let me write it therefore in this algorithmic way. Maybe I'll write it here because I might need some space. So maybe the input I will write still here. So the input for this algorithm is the sum choice of seed operator, the Hamiltonian, the associated Hilbert space, if you want, H. And I could sort of say that by giving you the inner product. Okay. So we, in this context, often call this guy the seed operator. Okay. This is our Hamiltonian. Sorry, this was just 2 slots open. And this is, for example, our choice of inner product. Okay, very good. So now what you do is you now define a number of steps. So first, you say that O0, which I also just denoted by 0 here, is 1 over the norm of O, norm using the inner product, times the bare state O. O is always this calligraphic O, but it means the operator. And now, 2, you construct some auxiliary state, which is just the commutator of the Hamiltonian with O, 0. And you then define the first Lanczos coefficient, B1, which is just the norm of A1. Okay. And therefore, you can now define O1 to be the normalized version of A1 using this B1 Lanczos coefficient. Now, I should say, by the way, I'm doing this a little bit schematic, and I'm trying to be less technical. In reality, if you talk about this version here, where the Hilbert space is the Hilbert space of operators acting on your physical Hilbert space, you should really think not about the Hamiltonian, but about the Liouvillean. The Liouvillean is a superoperator which basically implements the commutation with the Hamiltonian. And these things can be written, I think, more mathematically, succinctly and correctly, but I didn't want to go into necessarily this language. So I'm writing this here a little bit schematically. And also, I think it's more physically clear what's happening. And then the next step in this iteration is basically the general step in this iteration. So you construct the spaces now for n greater 1 by basically iterating this Lanczos algorithm. And it states that an is equal to h with O n minus 1 minus the b n minus 1 Lanczos coefficient, which you know, on O n minus 2. And at this step, you can then define the bn Lanczos coefficient, which is equal to an, and you can define the On basis element, which is 1 over the bn Lanczos coefficient times an. Okay. I have to say also, I'm always a little wary lecturing about this because you have to say all the time Lanczos coefficient, and I think that's a very difficult thing to say, and I usually get it wrong. But so now the statement is that this output of this, so we have the input is our physical system essentially with a choice of inner product. The output is now, well, two things. So you have the sequence of the B coefficients, B1, B2, up to, let's say, Bk minus 1. K will be the dimension of the Krylov space. And this is what we call the Lanczos sequence. And the second output is what I promised before, is this basis, orthogonalized basis of, well, we said O0, O1, O2, and so on, up to OK minus 1, which I also called just 0, 1, and so on. Okay? And so this is this thing here is the famous Krylov basis. And now for us, the point is the following. So for them back then, I think the point was that thinking about this iterative procedure of constructing a basis and constructing this sequence here is actually leads to very efficient numerical methods in linear algebra, and that are actually also widely used. But for us, it's actually something physical. For us, what we're going to do is we're going to, and I remind you, last time we thought about the idea of spreading of operators, and we're talking about the fact that there should be some canonical way of measuring the spread of operators. And I said that the right way to do it was to measure it with respect to the so-called Krylov basis. Well, here it is now, so this is what we will do. And moreover, we have this second source of information about our system. In our case, usually chaotic systems, but of course you could also do this for integrable systems. And you have this information that is in the behavior of the Lanczos sequence. And the behavior of the Lanczos sequence gives you insight into the underlying properties of the system. And so one of the things that was already, of course, designed by these authors was that the dynamics now becomes very simplified. So in this basis, or I could maybe say in this language, dynamics is simple. And the reason is actually that the reason is that the Hamiltonian, or in this, as I was saying before, really here, the Liouvillean is tridiagonal. And in particular, I can write the equation of motion. So if I define the wave function phi n of t is now the O operator O projected onto the basis On. So O of t now the Heisenberg operator, and I measure it in the basis On. This now satisfies a very nice and very simple equation, which is that minus I phi n dot of t is equal to b n phi n minus 1 of t plus b n plus 1 phi n plus 1 t. So you see that it's tridiagonal, in this case with zeros down the diagonal. And you also see that it is, in some sense, a simple hopping problem along this chain n, which we also like to call the Krylov chain. So this is, okay, I can even put a box around it. So this is now the equation that actually governs the spread of this operator, that tells us how we measure its size as a function of time. And what you see is that it's a simple, well, I shouldn't say that because simple always depends on people's opinions, but it's a hopping Hamiltonian on the Krylov chain. So just some quantum mechanical problem. And in particular, we think of the Krylov chain, you have your points, which we can label by the basis elements. So here, O0, O1, O3, OK, up to OK minus 1. And what you see is that there is terms that tell you how you hop from n to n plus 1. And these are the b n plus 1s. And then there are also terms that tell you, the reverse hopping, which are basically also the Lanczos elements, the elements of the Lanczos sequence. So time evolution here, I guess I already said this, but it bears repeating, is equal to, well, gives you the physics of operator growth. And is simply a hopping problem. There I said it again, simply a hopping problem on the Krylov chain. Okay, and now comes, I guess, our physical input or our physical intuition, which, however, I do think makes a lot of sense. As the operator spreads, it goes, to have support. So you started out with an initial condition that it starts at this point here. The wave function is localized here because you start with O0. And then this hopping will make it spread and possibly also disperse over the chain. And you say that it has a tendency to be more complex, involve more and more commutators, more and more of the basic elements of your quantum system. If it's, for example, a multi-qubit system, it will contain more and more operators that act on the different qubits of the system. And you say it gets more and more complex. So the natural notion of complexity to define then is K complexity or Krylov complexity. K complexity which the literature typically denotes as Ck of t, and it's defined as the expectation of the position along the Krylov chain, so n phi n of t squared. So this just measures where predominantly on the Krylov chain you are localized. For this quantum mechanical hopping problem, it asks where are you located on average on this Krylov chain, on average meaning in a quantum mechanical sense. And it says that basically you go from a simple thing to a complex thing by essentially this idea of spreading out on the Krylov chain. So O of t, somewhere here, this was my O0, and of course we could actually write it in this notation. And what we're saying is that it somehow spreads out, as it goes on along the Krylov chain. All right, so now this is now I introduced it somehow both, let's say, mathematically it comes from, as I said, it comes from numerics. It's a very natural and efficient way of doing numerics. But I've also given, I think, some physical, let's say, bias or intuition of what we should define as complexity. But that bias does actually come exactly from the elementary idea of measuring the size of an operator as it spreads out. Okay, so, I would say that the proof of the utility of this comes, of course, from the applications. The fact that this is actually useful, okay, and it is useful in all of the contexts that are in the title of my lectures. So that's something that, at least in part, I would like to explore also for the remainder of the lectures. Now, I'll make some comments, and of course, we can, let me first make a few comments and then we'll maybe pause for some questions. First of all, maybe I should ask, is it clear what I defined here, this K complexity, roughly speaking, what it is?
So what is the coefficient?
Which coefficient?
You multiplied n to the...
Phi n squared, absolute value of the wave function squared.
Yeah, before that.
N. N is just the, if you have the, this is just the expected value of position, right? If you had a quantum mechanical problem, you wanted to know where it has wave function phi of x, how would you say, what's the expectation value of x? Well, it's the integral of x wave function absolute value squared dx. So this is the same thing, but n being now the position along this discrete Krylov chain. And you could, of course, if you want, just define a position operator, which just would be n outer product. N and n outer product.
And in quantum field theory, the space must be finite dimensional, Euler space, so it can be arbitrary quantum field theory.
Sorry, can you say exactly what your question is?
Can you apply this for arbitrary quantum field theory?
Well, I haven't here because I've been just looking at many-body context where I just have some many-body Hamiltonian. But it is true that this notion lends itself also to looking at quantum field theory. The problem is that there you need to start regulating things. And it does become much more subtle, I would say. So I haven't like personally worked on this a lot, but I think it's certainly one of the promising directions to go into, because in principle, you can just take again some local window, microcanonical window of states, and then you have to find a good regulator for this inner product, and you can try to compute away. Now, people have done this, for example, in two-dimensional field theories. They have done this in two-dimensional CFTs, and they have gotten some promising results. But I would say that the answer, can you do it for arbitrary quantum field theories? I certainly don't know if that's at this point possible, right?
But you said you want to apply this to gravity.
Yes, yeah. Let's talk about it when we talk about gravity. Then, yeah, I do. Okay. So, other questions?
Just a very naive one. Is the length of the Langshot sequence and the field of basis K, is it related to the dimension of the hyperspace in any way, or is it?
It is. It's in this case here. It's related to the dimension of the Hilbert space H hat, and you can bound it using that dimension, and which of course is the square of the dimension of the original Hilbert space. Yeah. There's a strict bound.
But it depends on the operator.
Well, it depends whether you will get there. Depends on the choice of the operator. But in practice, it has an upper bound for any operator.
Okay. Thank you.
So, do all the notions of complexity that you define, like size and OTOC, complement with this?
Yes. I would say that in some sense, size complexity is very similar, and at early times behaves very similarly, but at late times, size complexity basically saturates much earlier, because it saturates at a much lower bound, which is essentially the number of operators, the total number of degrees of freedom, whereas here you can go exponentially later and have non-trivial evolution. And OTOC, well, again, in the sense that OTOC is sort of informally a measure of growth of operators. And you can, as I said already last time, for example, recover things like the Lyapunov behavior of OTOCs also by looking, in this case, properties of the Lanchor sequence Bn. So there are overlaps, but I think that this is sort of the richest framework which kind of encompasses the others.
What about non-local operators, where size can tell you that the operator is already very complex?
Yeah, so that's a notion in general that is a bit difficult to really answer, because I said simple at some point, and I sort of defined what is a simple operator. Actually, what this gives you is only a profile of complexity relative to what you started with, and you sort of automatically define what you started with as simple in that sense. So I don't think, to my knowledge anyway, that it is able to define an absolute notion of complexity. But I think that's actually, in some sense, a defect of most notions of complexity that I'm aware of. Okay, well, yeah, last question maybe, because I do need to go on.
I think along the same lines, in an OTOC, you need an insertion of a second operator, and then you calculate the overlap. So that's the intuition that I have, that in order to understand the spread of an operator, you still need another local operator to understand its growth. Is there like an intuition in K complexity?
Not really, to be honest, but I would say that perhaps the point that you're making is that is simply, if you want to use a correlation function to measure the growth of an operator, then you need a second operator. Right. Here you can actually measure it using this framework without needing to insert the second operator. And there is, as I said, there is this slope of the asymptotic growth of the Lanchor coefficients with n, which relates to the Lyapunov exponent. So what you say, I think, is more related to the fact related to wanting to measure the Lyapunov exponent or the growth of the operator using a correlation function. And then you need the commutator. Okay, great. So let me go on and make some comments. So there exists an analogous construction. I already noticed. I already mentioned this for states, and in this case it is often referred to as spread complexity. And there's one interesting change here, which is that, well, it is really in principle analogous. You have now, you take some reference state psi 0 and you look at the span of H and its powers acting on psi 0. Okay? But now in the process of tridiagonalizing the Hamiltonian, now not the Liouvillean, but actually the Hamiltonian, you get two sets of Lanczos coefficients. So you get A1, A2, A3, A k minus 1, and you get the B sequence, B2, B3, bk minus 1. And basically these are the diagonal elements here. So it's still diagonal, but this is, in this case, there are non-trivial coefficients on the diagonal. But then you get a very similar story. H is now tridiagonal in this basis. And the Krylov algorithm 1, 2, 3 goes through by adding a diagonal term on the IN. So as we like to sometimes write in textbooks, mutatis mutandis, so you only have to make the small change that there is also an AN diagonal component. Now, the next comment is the relation to OTOC and Lyapunov. So I can erase this. So, second comment is relation to OTOC exponent. So basically, it's a conjecture that if you look at the asymptotic growth in n of the Bn sequence in the thermodynamic limit, then first of all, this is in a chaotic system. Will be asymptotically linear, so Bn will go like alpha n plus order 1. And moreover, the complexity this corresponds to that goes like e to the 2 alpha t. And then this conjecture, or also known as the universal operator growth hypothesis, due to Ehud Altman and group, Kao, Parker, and I think maybe some other people also in his group, says that lambda, the Lyapunov exponent, is actually strictly bounded by 2 alpha. So the exponential growth of the K complexity in this limit is indeed related to the Lyapunov effect that we saw from the OTOC. Now this, okay, I call it a conjecture, and they called it universal operator growth hypothesis. If you take the infinite temperature limit in certain chaotic quantum mechanical systems, this has been shown to be true. So for example, in SYK. But in general, for finite temperature, so finite temperature comes in for the inner product, okay? This is still an open but plausible, a very plausible conjecture. So the third comment will be about, well, just a little bit more about its relation to quantum chaos. So So here, what I want to say is that essentially in a quantum chaotic system which has a finite effective Hilbert space, so for finite, so by effective I also mean that we can look at, again, this idea of just looking at a finite window of states at a microcanonical energy E, you can show to some extent, so this has been shown in many systems, it's been argued to be very plausible more generally, but again, making statements about quantum chaotic systems very generally is extremely hard. But basically you have the following behavior of the Bn, the Lanczos sequence. So you have this sort of rising ascent, linear ascent behavior, which in a finite, in the thermodynamic limit would go on forever, but is actually cut off in a system, finite system at order entropy or order number of degrees of freedom, which is then, gives way to what some people have called a plateau phase, but actually what you have is a very, very slow decrease to go to zero with a non-perturbatively small slope, and it goes to zero at order e to the number of degrees of freedom, e to the s. And this is the descent phase. And the idea here, okay, this is the Bn against n, okay? And the idea would be that these different phases of the behavior of the Lanczos coefficients basically also have their imprint on the K complexity, which then has the following phases of behavior against time. So now, there is often the let's say, dichotomy of talking about the behavior of the Lanczos sequence, which you can analyze for asymptotically large n, this size of the chain, but the complexity, of course, is naturally a function of time. So here we talk about asymptotically large time, and obviously those are not the same thing. You have to translate from n to the dynamics to get from the sequence Bn to the complexity Ck of t. That was a bit of a trivial comment, but sometimes it's easy to confound the two. So this has now exponential behavior at early times, which we already said, which is sort of like the scrambling phase. This exponential behavior, like e to the 2 alpha t, goes until the scrambling time of order persists until the scrambling time of order log s. It's then followed by a linear phase of growth. This is linear growth in time, okay, until times of order e to the s, at which point the complexity actually saturates. Complexity actually saturates and has some sort of plateau phase here. And so the game that one might one might want to play, and that we will play, is that you again associate the different in time phases of behavior of the Lanczos sequence with certain signatures of the quantum chaotic behavior of the system. For example, I already said that this has to do with the physics of scrambling. This is the fact that now, for example, post-scrambling, Krylov complexity shows linear growing behavior. Size complexity would already have saturated. And then there is a plateau phase. And for example, it has been explored a lot, whether, for example, from the properties of this plateau, you could distinguish, for example, again, something like the spectrum of an integrable system from a spectrum of a chaotic system. Of course, in an integrable system, also these phases will differ, but the size of the plateau, for example, would be an interesting quantity to look at in this distinction. And the last thing I want to say before I go actually and start talking about the subject of gravity is precisely comment number 4, namely that looking at this and having followed the sort of long sequence of papers that were essentially motivated by a gravitational point of view, thinking about complexity, this is exactly the kind of behavior of complexity that you want for what we call nowadays holographic complexity, meaning the complexity, let's say, associated to a black hole. And the big advantage here, your comment notwithstanding, is that this is actually now the property of a well-defined notion of complexity that really is a first principles notion of complexity and not some, let's say, somewhat vague notion. So for the point is that, I'm saying something now already using some jargon, which hopefully we can explain later on, but from a gravitational point of view, so this is, if you want, sort of a lightning tour of the different horizons of K complexity currently and what people are working on and what I find interesting. In gravity, you can actually show that this Krylov basis itself is extremely natural. And here, unfortunately, so far, this is only true about low dimensions. So in actually strictly, it only works in two-dimensional gravity. But I'll make some comments about that, of course, when we get there. But the Krylov basis is basically precisely the basis that you should use to construct the Hilbert space of the gravitational system. And it's there known as the chord basis of the quantum gravitational Hilbert space. So actually this Krylov basis also from the point of view of gravity in the context that I will introduce is not some random choice that came from some numerics papers, but it is actually the natural choice to write bulk observables. And so what this is saying is, bulk meaning gravity, by the way, gravity observables. So what this is saying is that actually there is some sort of geometric view on this. So now I'm going to just draw a diagram. Those of you who are familiar with gravity already will recognize this as the Penrose diagram of an ADS black hole. So you have the famous horizon of the black hole. You have the right exterior and the left exterior. And if you measure the distance or a measure of volume between, so this will be anchored at time t, so time, let's say, goes upwards here in both directions. If you measure the distance or, in higher dimensions, the volume of a slice that goes as anchored between these two times, and how it depends on time, so this is the size of this bulk gravity slice. Actually, the size as a function of time is basically ck as a function of time. Okay, so in this sense, what you get is you get like, and I of course have to still do the work for this, but you get a precise notion of complexity geometry relation. So I have some time still. I still want to go on and introduce some of the background we need to understand this gravitational thing. I was just going to say that my original plan was to say something about each of those comments, I mean, in more detail. But as I have only one lecture left, I prefer to tell you about this because that's actually personally what I'm most excited about. So that's what I'm going to do. But of course, we can also discuss in the questions and in the discussion section other aspects of this. Okay, so this was my lightning exposure of this, as I said by now, rather rich subject of Krylov complexity. I will again say that there exists actually now a couple of reviews, but in particular one that we wrote very recently. So any of these aspects, if you're interested, there is a lot of detail in there, so feel free to study it there, and please also, of course, feel free to approach me if you have any questions about any of these aspects here. Okay, so I do want to push on a little bit. We can have questions at the very end of this lecture, because I feel like if I open it now for questions, we will just spend the rest of the lecture discussing the questions. You always have very good questions. So let me go on to the last part, which is basically yeah, there's not just complexity. There's several of the notions that I talked about before. Gravity and with a little bit tongue-in-cheek, I can call it the bulk of the story. So the idea is the following now, is that I want to at least convince you that it's that black holes are chaotic systems. So we're basically starting now, again, at the beginning of my set of lectures. But now I'm going to tell you that black holes are such chaotic systems. And then I want to also convince you that thinking about black holes is actually a very useful way of generating knowledge about gravity more generally. And thirdly, I want to convince you that these notions of chaotic dynamics and eventually complexity are actually a very interesting and source of many insights when thinking about gravity. So let's start with this statement that black holes are chaotic systems. So the intuitive argument is actually the following: is that it's known that black holes define a thermodynamic partition function. And basically goes back to work of Gibbons and Hawking. So the black hole itself should be associated with a density matrix, which is actually e to the minus 1 over the Bekenstein-Hawking temperature times the Hamiltonian. So in what sense we should think of this Hamiltonian, I will clarify as we go on now. But the idea is essentially that correlation functions, have this thermal correlation functions have this property that they satisfy the KMS condition, that basically they are periodic on translation in imaginary time, if you start with a black hole, you have, of course, time and you have space, and they are in a signature minus, plus, 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 and if you want more dimensions, you can add them here. This would be time, and this would be space, and that would correspond to some diagram of the type that I just drew here. But in fact, you can, of course, also mathematically think about Euclideanizing it or doing a Wick rotation of the black hole. And you find a geometry which is now in purely positive signature. Okay, it's a Euclidean thing. And it turns out that this was time, now this is Euclidean time. So this was tau, a t, and this is maybe tau is equal to it in here. It turns out that because of very basic properties of the geometry of black holes, this Euclidean solution makes no sense unless tau is equivalent to tau plus beta, meaning that now I have to identify periodically Euclidean time. And it makes no sense in the following way. It says that this black hole is actually singular at what used to be the horizon. So if not, so tau has to be proportional to tau plus beta to avoid a pathological spacetime. So this is a kind of a singularity that you cannot make sense of. It's not just a coordinate singularity. And so in some sense, these black holes have built into them that if you want to look at their statistical physics, meaning you look at them in Euclidean time, in Euclidean signature, then everything becomes periodic with respect to imaginary time. And if you actually go through this, you can prove that all correlation functions satisfy all correlation functions of anything that moves on the background of this black hole. Like you might measure some Hawking radiation, or you might measure any other quanta around the black hole, has to be periodic in Euclidean time with a very particular period, and that period is actually precisely the temperature of the black hole, or rather the inverse temperature of the black hole. So beta Bekenstein-Hawking is just 1 over the temperature. Let's call it the Hawking temperature. Okay, so so I could derive that for you. Maybe even if you want during the tutorial session. It's actually not as complicated as it might sound. It's quite a slick derivation. But let me just go on with my argument. What I really wanted to say. So you really should think of the black hole as being an object which, for every observer, basically puts the observer. Well, for observers. Puts the observer into a thermal density matrix. It's not every observer. Strike that sentence. But for observers that perceive a certain natural notion of time. Okay. So now, once the black hole is there, you are in a thermal state. So you have thermalized. And now the thing that I want to say is that it is also known that a typical initial condition, or a generic, I should say. 1 second. A generic initial condition leads to black hole formation. So the idea is that generically things thermalize. But now first, yeah, let's have the question, yeah.
The Hamiltonian, what is the Hamiltonian?
Yeah, so the cleanest way of doing it is in ADS, it will be the Hamiltonian, which is dual to the killing time on the boundary of ADS. But it also can be, for example, the Hamiltonian that is dual to the killing time of an asymptotic Schwarzschild observer. It's certainly not the Hamiltonian of the observer that falls into the black hole. That's why I actually took back the statement that everybody receives thermal radiation. Something like that, yes. Again, I mean, I say something like that because the infalling observer that is in free fall in the black hole, that does not work. But if you take, for example, well, asymptotic observers that move according to killing time of Schwarzschild, then it's true. Yeah. But let's talk about it later. You seem to know more about this than is appropriate at this level of detail. So now the point is that a generic initial condition or generic initial data actually leads to black hole formation. That's something which, of course, has reached a lot of attention because Penrose notably won the physics Nobel for this kind of statement. But what is the statement? The statement is that if I take a slice of data at some initial time, t is equal to t initial, and I set up the system with some excess energy, I mean, the typical thing that people will talk about is literally stellar collapse. Like you have some star that is at the end of its life and that contracts under its own gravity. But you could also set up some initial burst of gravitational radiation that converges, some kind of initial condition of excess energy over the ground state energy. So let's say something like stellar collapse. Okay, then this will eventually lead to contraction and the formation of a horizon. So this is like the formation. So if time goes up, as it did also in the previous lecture, time goes up in high energy physics and also apparently in gravity, then what you have is a horizon formation and eventually even formation of a singularity. So this is like black hole formation. Okay, but the statement is, so I'm using the astrophysical terms here because this is how the literature talks about it, but the statement that I want to make is that if I set up the initial state at t is equal to t initial, and I should think of this as specifying some rho density matrix initial for the system, something like this, which may just be a highly excited state, a non-equilibrium state, then generic initial conditions actually lead to the formation of the black hole. And the black hole I just argued is actually a thermal system. So the black hole is a thermal system. So in other words, gravity, or I should really have said semi-classical gravity, but gravity is one of those systems, is a thermalizing system. And you might even say that in this sense it's a system which is classically thermalizing because I told you essentially semi-classical stories. And such systems are typically associated, as we said at the very beginning, to the classical notions of chaos, such as Lyapunov instabilities, such as the dynamics of mixing and ergodicity. So it is very natural to expect that this whole thing actually is an example of our chaotic systems. And it actually turns out that, I mean, I gave you an intuitive argument why this should be true. It actually turns out that at least in a specific context of the so-called holographic duality, we can make this absolutely precise. So I'm saying now this suggests that quantum gravity should show signatures of, first of all, let's say, local thermalization, of scrambling or Lyapunov, let's say, of random matrix physics and of ETH-type physics. And it turns out that all of these things are actually true. And I will hopefully be able to use the last lecture to tell you some aspects of this. So all of these things actually turn out to be true. But to show that they are true, we need to go to this, so can establish maybe we should also say some interesting complexity growth. Okay, this is the last thing that also we want to show, and that is also true. But can establish this for gravity in ADS, where ADS is this famous anti-de Sitter space, which I will introduce, and it allows us to treat gravity using this idea of holographic duality. Okay, so we have quite a menu for the last lecture, but I will try to give you at least a taster of how these things work. And so the last point, of course, is that I will try to argue to you, which is definitely the case, and which is why I and many others are so excited about this, is not that you go and you kind of tick off a list of things that should be true. Actually, especially in this thing here, you really learn new things about gravity that you didn't know before, and that establish basically this thinking in a chaotic way about gravity as something that's extremely useful. So in view of time, I'll stop here, and of course I'm open for your questions. Yeah.
So question one is you considering about your lower dimensional gravity, and you mentioned that it's two-dimensional, but for the two-dimensional, it seems that people don't have a black hole in your, so it seems that if you want to consider about the black hole, the two-dimensional gravity. Thanks.
I mean, I can repeat the question, I think. So the question was that some of the things that I'm talking about, essentially only the very last part here can be established rigorously only in 2 dimensions. I mean, I can talk about these things also in higher dimensions where your question doesn't arise. So the question was that in 2 dimensions there isn't a real black hole, which I agree with, but actually all the computations are done in such a way that you use properties of the BTZ metric, which is a 3-dimensional metric, and essentially reduce it to 2 dimensions. And so I think, for example, and I'm pretty sure that we can establish this, that those things are also true about the 3-dimensional BTZ black hole, in which case your objection isn't really valid.
And I have another question that you want to connect the Krylov complexity with the holographic complexity, but as you mentioned yesterday, because the holographic complexity, all kinds of complexities.
Can you talk into the microphone?
Oh, sorry. Because for the holographic complexity, all kinds of different kinds of complexity, they have a definition about simple hard operator or something, as you mentioned yesterday. But for the Krylov complexity, people don't have things like that, so the definition is quite different. So what's the main idea to connect the 2 sides with the holographic complexity and the Krylov complexity?
Well, that's very simple to say. I mean, the point is the one I made. Maybe I raised it, but the Krylov basis actually turns out to be the most natural basis to describe the Bell-Hilbert space, and we can directly translate the Krylov dynamics to the bulk dynamics in this case. So it's actually much more direct than the other ideas that you mentioned.
But for the holographic, we always have all kinds of complexities. So
yes.
It means that you only choose one complexity. Fix very well.
I don't know what exactly you mean by you choose, but I am proposing that there is one that works.
Okay, thanks.
No, wait for the microphone. Thanks.
Can you just tell me what is the dual of this statement that a generic initial condition leads to a black hole formation for the dual
statement,
CFT?
It's a statement that generically the the dual theories are chaotic and they thermalize. So they reach, the black hole would be like a locally thermalized state. So the horizon formation corresponds to this stage of thermalization, but indeed we can also follow these other ones at later times, and we find that they also are present as the gravitational signatures of each of these.
So these properties will be present only for those CFTs which has a holographic dual, but not generically?
No, that's not true actually, but there are certain aspects of this which are true only for holographic CFTs. So, for example, the fact that this is an extremely fast process, people talk about it as instant thermalization. The fact that scrambling saturates the bound that I already hinted to, so that actually the Lyapunov exponent is equal to 2 pi over beta. And then there are also aspects here which make it special in gravity. But of course, you can think of many field theories that show all of these behaviors that are not dual to some holographic setup, but they will still have interesting chaotic dynamics. Yeah, but they don't saturate. The idea would be that in some sense these things are extreme. They have like the instant local thermalization, they have the fastest possible scrambling behavior, and they have, let's say, the fastest possible Taylor's time in the class of theories that they are. And the hope is indeed that might be a set of conditions that you need to put on a field theory in order to ensure that it has a holographic dual. But whether that's true or not is still under investigation.
Thank you.
I'm sorry I'm asking this question after you erase it, but if we have Lanczos algorithm, we also have like a non-Hermitian version.
We have a what?
Non-Hermitian version, like Arnoldi method, yes?
Yes.
Could you tell if about the because as I understand, you can correct me, non-Hermitian is like influence from the outside. So
is what is a influence?
Can account for the influence from the outside. So
yes.
So I was thinking about this like black hole, and we treat it as isolated, right?
That's right.
Yeah. So
for now, anyway.
Yeah. So this Hamiltonian is we assume is Hermitian.
Correct.
But if you would like to have, for example, I don't know, Hawking radiation, and like I don't know, so some like some externality to this. This could how would this procedure change? Could you tell us?
So first of all, people have been thinking about these Lanczos approaches for non-Hermitian systems. And so I'm not focusing on that, but the other review that's out there actually talks about that, among other things. So as you say, you can use this Arnoldi method and so on, but I'll refer you to those papers in that review for that aspect. But let me just clarify one thing about, so it is not needed in order to describe something like Hawking radiation to go to non-Hermitian setups. So typically, what you have is you will have like people even draw it as some sort of a container. It's like a perfectly contained system where inside of it you might have a black hole, which I will draw like this, and this black hole can radiate. And this black hole Hawking radiates, but the Hamiltonian that describes time evolution is perfectly Hermitian, and the point is that the black hole and then its thermal environment are perfectly enclosed. There are perfectly reflecting boundary conditions, and the dynamics is unitary. If you were to, for example, trace out what is inside the black hole and only look at the outside, now you might think of the outside as an open system, which has, a right to be described by a non-Hermitian evolution law. But the fact that you have the black hole, everything that's inside and it radiates outside, is like you take a system that thermalizes as part of a global system that is in a pure state and is evolved by a unitary quantum rule. Okay. The last thing I will say is that nevertheless, people in recent years have extended this picture. So this is now a perfectly enclosed black hole, but people have actually done something where they now couple this to a bath. So now everything that's outside this cylinder would be an auxiliary bath system, and they couple it to a bath. And now the Hawking radiation that comes out of this can actually escape into the bath. And this bath radiation system, now if you integrate out the bath, you should think of this as an open system with non-Hermitian dynamics, and there's actually very interesting things that can be said about this. But that's not something that I'm going to talk about in my lectures. But it would be interesting, and people have indeed thought about this Arnoldi method in this context.
Okay, great. So let's thank Julian again, and I believe we have lunch outside.